Good morning, everyone. We have covered axial forces and axial stresses. Then we have covered torques and torsional or shear stresses, and then twist. Today we are going to start on bending stress. Right. So what will happen today is we will give you very, not quantitative but qualitative idea about bending stress. What is a bending stress and how it acts on a structure, and what forms of calculations we are going to do, what are the assumptions behind it. These are the things that will be covered in today's class. Next class we will be covering into more details about the quantitative part of bending stresses. Okay, so here is my first slide. As usual, it tells you what are the things that are there in the syllabus. BMD SFD is part of the syllabus, which you have already learned in your engineering mechanics course. Right, so this is important for us to go through. And then you have to learn bending stress, its definition and its quantitative understanding, qualitative and quantitative understanding. Then comes the shear stresses in beams, which will also have a qualitative and quantitative understanding. Then we will use those understanding to composite beams, right? And then we will move into shear strain in bending. And also we will learn in shear flow, during shear stresses, we'll learn shear flow and shear center, which is an important part, which are few important parts for the design, like finding neutral axis and then finding the Newton planes, uh, and then probably also finding shear centers, right? So all those things are part of the design. So we will learn what are these things, okay? And finally, of course, there is a part which will deal with the deformation of beams, right? So how the flow works? The flow works from external load that you put on a beam moves to be calculated to be internal forces like bending moment and shear force. And once you know internal forces, you can find stresses. We'll define what bending stress is. And then from bending stress, you can find bending strain. And from bending strain, you can find deformations. So this is overall picture that we're going to learn in probably next few months. Okay. What do we mean by beam? That's the first thing that we have to understand. What do we mean by beam? Can you all hear me?
So
Yes, sir.
we can hear you.
Yeah, thanks. So if I have to write a beam, what do we mean by beam? Structurally, what are beams? So beams are members that carry transverse load, okay? Right? Remember transverse load. So they will carry transverse. Beam can carry axial load also. But if it has only an axial load, no transverse load, then it becomes an axial member. But a beam has to carry transverse load, and therefore there are transverse deformation. Okay, when I say transverse, what do I mean by transverse deformation? So let's say this is my beam structure. Okay, this is called axis of the beam. Let's say this is X. It is called longitudinal axis. Anything that is perpendicular to this are transverse. So it can be this direction movement also, or it can be this direction movement also, right? Y and Z are transverse axis. Okay, Y is called in plane. And Z is called out of plane. Why it is called in plane? Because my cross section will be something like this. This is my Z. This is my Y. So bigger dimension is towards Y. This is D. Okay. So that's why it is called in plane.
Sir,
Yes.
so what dimensions towards Y, sir? Like you were saying.
What dimension in the sense?
No, like so you were saying like some dimensions towards Y, sir. Like
Yeah, I'll come to that. Yes. So when I have a beam, if I draw a beam in a little bit bigger format or exaggerated format, right? So let's say this is beam. Okay, let's say there is some support here. All right, this it's longitudinal axis. Okay, this is how you draw a beam, and then here it's cross section, right? So this is L. This is width, right? So width we'll write it as B, and this is called depth. We write it as D. Okay, now here you will have two axes, right? So one will be like this, other will be like this. Okay, this is my Z axis, and this is my Y axis, and this was my X axis, and this is cross section. Okay, so it's like this, it is something like this. In a 3D picture, it is like this. So this is that cross section. Right? Okay. So these are the dimensions and detailing of a beam. And when we say in plane, we mean that the loading will be somewhere here. The loading will be on this line. That means along this Y line there will be loading. Okay. So loading will be somewhere here. Deformation is along the loading in that direction Y. It's called in plane. If the deformation is along Z direction, that means this direction, this is not in plane, this is out of plane. Now let's look at how a beam deforms. Okay. Before we look into how a beam deforms, let us go into something called shear force and bending moment diagram. So if I have a beam and I have simply supported beam, two simple supports, and then I give a point load here, P. Okay, how will its bending moment diagram look like? Shear force diagram look like? Okay, let's draw it. Let me draw the shear force diagram first. So that's my baseline. My shear force diagram is going to be something like this. So it will be P by 2 here, and then there will be a drop by amount of P, then it will go like this, and then it will be a P by 2 here also, right? Am I right or wrong? This is positive, this is negative. Why is that positive and negative? Because it depends on my sign convention. If I change my sign convention, this positive and negative will change, right? What is my sign convention in that case? My sign convention is, if you see for shear force, the sign convention is going to be something like this. Remember, sign conventions are very important and you have to always do this. So my sign convention for shear force positive is down this way, up this way. Okay. So if you take a section, here, AA, section AA, then you have this section like that, right? Let's say this is my A point, this is my B point. So this is my A point and this is AA section. So you have here P by 2 and therefore this side it will be P by 2, right? So this acts as a positive shear. Okay, so this is a positive force. So I write it as positive. This is my sign convention. So that's positive. Whereas if you go to another section, which is BB, if I look at section BB, right, what do I get? I can draw it something on the other part only, right? So let me make some colors. So that will look good. Let's say this is the pink color, and then this portion is pink, right? I can again draw that portion of the section. So this is B. So this is BB, right, section, and that will be yellow colored. So I'm looking at the yellow colored portion. And if I look at the forces, it's going to be this side upward P by 2, of course, by the support. And therefore, this side it will be downward P by 2, right, to balance the force in the section. And therefore, its cross section is looking like this, shear force. So this is a negative shear force. Okay, right? Now, if you change your cross section, so many books will have a different different sign convention, right? So if you change your sign convention, things will change. Very simple. So don't worry about positive or negative, right? Check your sign convention, and based on that, it will be positive or negative. Now let's look at the bending moment diagram.
Sir,
Yes. Yeah,
sir,
tell me.
while solving questions, can we take the sign convention which we use? Like, should we mention it or can we
You
directly
have to
use it?
mention whatever sign convention you take. You have to mention.
So, okay, so we need to draw the small picture, so like square plus
Uh,
that we need to draw and solve this.
yes.
Okay.
Now let's look at bending moment diagram. So bending moment diagram is going to be all positive, right? All of you agree on that? So it will be 0 here, and then it will come like this to a point here where the load is acting, and then it will go down to where it is, man. So disrupting. So it will go like that, right? So this is going to be your bending moment diagram. Now, please note that I have drawn my bending moment diagram positive downward. Okay, so this is the convention I'm going to follow. It's up to you whether you follow this convention or not. But this is my convention. I am going to draw my bending moment diagram always positive downward. The reason will be clear as you go on solving a few problems in the semester. You will see that drawing the positive drawing downward is a bit helpful in understanding the deformations of beams. Okay, so we are going to draw this positive downward. Now, why is this positive? My sign convention is, so what sign convention leads me to positive value? My sign convention for moment is, this is positive. Okay, all right. So let's take again section AA and analyze it. Section AA. Okay, so I have this beam, and this is point A, and I have a load P by 2 here. So what will be the moment here to balance it? From this point, if you take from this point, if you take this moment with this momentum, this moment is going to be like this, right? To balance it, there has to be a counterclockwise moment that will act here. So its free body diagram is going to look like into x, if this is x. Okay. So therefore, if you take a section here, small section, that section will going to have what happened. Like this, right? Moment. All right, so this is my positive. So that's positive moment, positive bending moment. Similarly, you can check at BB and you will get again positive bending moment, because this one from this point will give a force like this, moment like this, and therefore there has to be a moment that will act here. So that's also going to be positive bending. So let's let's write it. When we're writing, we will write that. So section BB and there is a force here P by 2 acting. Therefore, to balance it, there has to be a moment that is acting this side, which will be P by 2 into x. Let's say this distance is x. Therefore, if you look at a portion which is very small here, like this portion, you will find that this type is M, side is also M. And therefore, that's positive bending moment. Okay, is that clear? Okay, let's take another example here. This is very important example. I have another beam here. Okay, A and B, and I have support here. Same simple support, okay, right? And now I have two loads. One is acting here, which is value is P, and another load here, which is also value of P. Let's say this distance is L by 4, and this distance is also L by 4. Okay. Now, how its shear force diagram and bending moment diagram going to look like? Can you please draw quickly? Shear force and bending moment diagrams. Huh? Anyone? Drawn? Right. So let us draw it. For shear force diagram. Okay. The shear force diagram at this point A, the support action is P, right? So it's going to go up P because this side is going to be positive. So this is positive P. And then after coming to this point, there is a downward force P acting, right? So it has to come to downward side by value P. So it has gone up by value P here and gone down by value P here. So it's going to be 0 at point C on the right of C, right? And since there is no force acting, it will continue to be 0. But at D, there is another downward force P acting. So it will go down by P again, right? And then it will continue to be at P because there is no force acting between D and B. And at B, again, there is a support reaction. P will act upward. So it will go up like this, right? So it's going to be again negative on this side and positive on that side. And in between, there is a 0 shear force. Okay. Right. Now, for bending moment diagram, how we draw? Bending moment diagram is going to be P4, there is moment 0 here because the support will have 0 force, 0 moment. And there is a P4, so it's going to increase like P here with a slope of P. So this is P into X sort of thing. Then this will be, P into X minus P into L by 4. That is going to be here, right? And that's going to be a constant value, right? So what is this portion? This portion is P into X minus P into what should I write here? So one will be P into X, the other will be P into X minus L by 4, right? And that is going to be your P into L by 4, right? So it's going to be a constant value. So this value is P into L by 4. So it's going to be constant because there is no force or moment acting in between. So it's going to get constant, and from there it will again fall down and go to 0. So that's going to be your bending moment diagram, right? And it's all positive. You check it, it's all going to be positive. And as I said, I draw positive on the downward side. It's going to be positive on the downward axis. So my positive axis is downward. Okay, so this is positive, this is negative. Now, the middle portion is very interesting. This middle portion has bending moment, but no shear force. So let's write it. Section C to D has 0 shear force, right? As constant bending moment. This is called pure bending case. You have heard it before also. I'm sure you have heard it before. This is called pure bending case. Since there is no shear force that is acting, only bending moment in that portion of the section. And this is very important for bending stress discussion. Okay. This kind of bending, this example that is given here is called 4-point bending. What is a 4-point bending? There is a point here, there is a point load here, there is a point load here, there is a point load here, right? So there is a P force, there is a P force, there is a P force, there is a P force. 4-point. This is called 4-point bending. So there is a test available for 4-point bending test because this gives a constant moment. Whatever deflection we do, whatever stresses we find for beams, they are based on pure bending condition, pure moment conditions, and therefore this is your pure bending portion, right? So we'll write this portion is pure bending portion, and that's important for our analysis. Okay, there are a few more examples for pure bending cases which you can probably go through yourself. One of them is you have this beam A to B and you have a moment here, send moment here. Okay, check whether this is also pure bending or not. All right, check these things. So good. So we understood how to draw bending moment diagrams and shear force diagrams, our sign conventions, and also we have understood what is a pure bending case, and that's very important. Pure bending is very important, and we cannot, live without that in this course. Pure bending. Okay. Now, why did I say pure bending? Let's come to a little bit more details, which is new for you now. Okay. So let's draw another beam here. Okay, it seems to be a too big a beam, but let us hang on with this for some time. So there is this support and there is this support, right? It's an exaggerated version of the beam. And now you have given some load to the beam. Maybe a point load, maybe UDL, whatever you want to do, you have done. What will happen? What do you think will happen? It will start bending, right? It will show some deformation. And what kind of deformation it will show? Since if my load is symmetric, first point, load is symmetric about the cross section. Okay, which means, what does that mean? Which means is I have to draw it a little bit down. That's all it means. Which means if I have the cross section like this of the beam, and this is my Y, this is my Z, then your load is here, symmetric to Y. So it is not creating any twist. Okay, which means not creating any twist. Not unsymmetric loading will create twist. Creating any, we don't say twist in beam, in beam, which is, let me write twist. Okay, twist. In beam we say out of plane bending, which is not creating any twist or any out of plane bending. Finish. First point over. Now second point is the beam is symmetric. Beam cross section is symmetric about y axis. Okay, very nice. If it's not symmetric, what will happen? Right now we don't know. We will deal with this later, as you know. So right now symmetric, they're symmetric. Okay, completely symmetric. That's what we know. Don't ask me what happens, because we will deal with this what happens later. We will develop these formulas later. So for now we will develop the formula for this case. Second is this. Third is, let us consider pure bending case. So no shear, zero shear. Okay, which means no shear force at that portion, wherever the portion you are looking at, there is no shear force there. Okay, then you might say, sir, then why is this load? Okay, forget it, this load is not there. I'm sorry, I draw this load, so let us remove all these loads. Okay, all right, and we have only two loads. Now you'll be happy, probably. Okay, so we are looking only at the pure bending case. So probably we are looking at only this portion of the beam. Don't ask me whether they are valid beyond that or not, because my answer will be yes, the formulas are approximately valid beyond that point also. Not approximately, very well valid after beyond that point also. But let us right now not go into that. We will deal with this whether they are valid in the shear force zone or not a little later, not now. So right now we are looking into pure bending case. Now when you load a structure like this, what are you going to see? What do you feel it will happen? It will start bending. All right, it will start deforming, and the deformation, if you grant me, is going to look like, it is going to deform like this. Right? Is that clear? The top portion is going to compress and the bottom portion is going to elongate. Very simple. Now, if the top portion compresses, reduction in length, and the bottom portion has increase in length, then there should be one portion where there is neither increase in length nor decrease in length. So let us write those phenomena. Okay, under the above loading, top fibers are compressed, bottom fibers are elongated, which means this means there is a fiber which neither elongates nor compresses, right? Okay, let me draw the picture again and see whether our understanding is clear or not. Copy and paste it back here. Paste. All right, so how its cross section, if I take a cross section, is going to look like? The cross section is going to look like this side is getting compressed. So, if I draw one cross section, before cross section was something like this. Not cross section. If I draw a section, before this was like this. After deformation, it has gone something like that. So this has elongated. This is the zero section, and this has compressed, right? Right. So the bottom portion, this portion, under tensile strain, which also means they are under tensile stress by Hooke's law. This portion is in compressive strain, compression or compressive stress. Right. So this fiber located here has neither elongated nor compressed, right? So there is strain is supposed to be zero. This location fiber is called neutral. Strain equal to zero. Okay, strain XX. YXX, I'll come. So there is this zone. All the fibers are neither going to elongate nor going to compress. This is called neutral axis. And the plane is called neutral plane. Okay, the plane is called neutral plane. Now, this neutral axis is very important. So what is the definition of neutral axis that we come down to? The definition of neutral axis is epsilon xs to 0. There is no strain on that any fiber in that axis or in that plane. Now, why do I call it plane? I do call it plane because generally they will be across also, right? So this will be the plane, right? Along which, so in the width side, there is the same plane will continue along the width, right? So that's plane. Now this is axis, the one line of the beam, this is axis, but when you draw a 3D picture, that becomes a plane, right? So it's called a neutral plane or a neutral axis, right? And its property is given by sigma epsilon xx to be equal to 0. Okay, so that's what happens when you load a structure. Now, why this is sigma xx? Why this is epsilon xx? Why it is epsilon xx? Because if you see my drawing, this was, so let me write the question first. Why epsilon xx? Bending stress or strain are normal stress or strain. Although the deformation is transverse, the stress or strain is normal, not shear. We know that there are only two kinds of strains and stresses are available, right? Normal and shear, right? So bending belongs to normal, not to shear. Why it belongs to normal is going to be clear now. So I'll paste that picture again. Oh, it doesn't allow me to paste. Okay, paste. Yeah, it allows. Fantastic. Now, why it is sigma xx? So let's look at fiber. So let us assume the beam is made up of fiber. So that was my beam. Any cross section of the beam, and it is made up of lot of fibers. So there is a fiber here, 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 right? Now when it compresses or tensile, get elongates. And what is this direction? This direction is my x, right? And that is my y. So that is my x direction. So these fibers are along x direction. And now we are telling that this fiber is going to be like this. So the fiber on the top side have compressed in length. So they have come up to that with red. They have to come that, they have come up this, they have come like this. There it is neutral, and here it is elongated, and here it is elongated. So this extension is epsilon along x direction, strain along x direction. Okay, so that's why it is sigma xx. So this has to be 0 for this is epsilon xx and sigma xx. Okay, this kind of bending where we have bending where we call this as sagging. Sagging, where section is under this kind of moment, compression at top, tension in the bottom. And it is called positive. So when we say sagging moment or sagging bending, we call it positive, compression at the top and tensile at the bottom. So this is also a nomenclature that is heavily used in industry. That's called sagging. When they call sagging moment, that means there is a tension in the bottom side of the filaments or the fibers, and there is a compression in the top sides of the fibers, right? Same thing will happen when you have a hogging moment. We call it hogging moment. Okay. Hogging moment means, as I said, this is going to be negative, right? So in that case, what is going to happen? You have this, again, you draw the beam. But now your moments are acting like this. All right. So there will be again a neutral axis, neutral plane. This is neutral axis. Okay. And it's going to bend tensile in the top and compression in the bottom side, right? So it's going to go like this. Okay, and this neutral axis is going to bend like this. So that side is tensile. Painting is very important, man. Childhood, I did not learn painting. I should have learned. I did not know any time in teaching this will be so important and an art to explain things. But yes, it's nice. I mean, when if you see these things after uh, 2 months or 1 month, you will remember exactly what Sal has told. What is this different color mentions? Because only drawing with one color and without painting, if I do it, it won't get into your head. Now you see, perfect. So so that side is compression and the other side is tension. And the line that doesn't change is the neutral axis line. This is called hogging moment. Okay, negative. But it has the same picture. Now, why do I say only pure moment case? If I talk about only pure moment case, we get this changes that you are seeing here, right? This changes, this bending is going to get circular. You can only get circular bending when you have pure bending case. We'll discuss more about this in the next class. Why pure bending, and then we will, so from the pure bending understanding, will we will quantitatively define the stresses and strains. Now, one more point before I leave, I want to say is, looking at bending, stress. Look at bending stress. So let's say that I have a cross section, right? And there is a neutral axis. Okay. And this side is, again, let me draw it. This side is yellow. So that is under compression. And this side is something like orange. So this is under tension, right? So this is sagging moment. And there is this moment M acting. Now, if I draw its cross section, when I say cross section, I mean cross section like this. Okay, looking at the cross section, cross section is going to look like this. Okay, this is your neutral plane. This is not neutral axis, this is neutral plane, because it is in the cross section, right? This is your neutral axis. We call it NA, and that is neutral plane. Now that side is compression, and this side is tension. Okay, so let's draw compression as circles. And let's draw tension as crosses. Right? So that's going to be compressive stress. So this side is compressive stress. Compressive stress. And this is going to be tensile stress. Okay. And now look at not the cross section, but a section. If I look at a section, looking at a section, okay. The section is going to look like this. And this is your neutral plane. And we said, we have shown that, at neutral plane, the strain is 0, and other planes, the strain is going to grow like linear, right? We have shown that with these figures. It's going to grow like, see, linear. So if we assume that to be linear still, what I'm going to get is something like this. My stress will also be something like that. So this is compressive stress, and this is tensile stress, right? And they're acting over this area. Okay, so they're acting over that area. So something like this. It is compressive here. but it is tensile here, right? Right? Now, if I know the maximum sigma T and sigma C here, the maximum, the top value, sigma C and sigma T, I can always integrate over the area and I'll get the force. And that force is obviously going to go from the center or centroid of the section, right? So it will go from there. So this is my sigma C and this is my sigma T. So this is going to be sigma C into area of cross section. Okay, you have to integrate it. Just don't write sigma C, integrate. And this is going to be your sigma T. Let's say, let us put that integration. And that's going to act again in the same position, but in the opposite direction, right? It's tensile. So this is F. This is also F. They have to be same. The total force has to be same, because otherwise it will elongate. If it's not same, then what will happen? It will start moving in the direction, right? If it's not same. So they have to balance it. The section is balanced. Right? The section is balanced, so they have to. So now this, the distance between them, let's say, is h. So total moment is going to be F into h, and that should be equal to your external bending moment. Right? If it is not equal to external bending moment, then the section is not balanced. To balance the section, the moment that is created by the stresses should be equal to the moment that is coming to the section, which is bending moment. Right? Otherwise, the beam will start rotating there if there is an unbalanced moment. Now, this quantification will make it more clear in the next class. Okay, but I've just given you a hint, a rough hint of how to roughly calculate bending moments. So now we don't know what is sigma values, right? We don't know the sigma values. Once we know sigma value, we can only then find this. Now, how to calculate that sigma value and how to relate that with bending moment is what we are going to learn in the next class. And this sigma value will be changing at different sections, right? It is, as you can see, it's changed along different sections. And we have assumed a linear right here. This linear is valid as long as you are in pure bending. Once you are not in pure bending and shear contribution is very high, it will not remain linear. It will start getting into higher orders. So something like this. So we'll talk about those things in the next class. I'll stop it here.